Hey everyone, welcome back to this channel. In today's video, we are exploring one of the most crucial aspects of operating systems, memory management. It's how your computer keeps track of all the data it needs to work with efficiently. Whether you are coding, watching a video, or browsing the web, your system has to manage memory effectively to ensure everything runs smoothly. So, let's dive into how memory management works, why it's essential, and what techniques are used to make it efficient. Memory management is the process of controlling and coordinating computer memory, which includes assigning memory blocks to different applications and reclaiming it when it's no longer needed. The goal is to keep your system responsive and prevent it from running out of memory, which could slow it down or even cause it to crash. Think of memory management as a smart organizer. Your systems keep track of what each program needs and allocates memory in a way that prevents overlap or interference between different programs. It's an ongoing balancing act that ensures each application has the resources it needs without taking up more than necessary. Imagine if you had a limited amount of space to work with, say only a few drawers, and you needed to store everything you would need for the day. You would need to be smart about what goes where and how you store things to avoid running out of space. Memory management does the same thing for your computer. It ensures that limited memory resources are used efficiently, preventing any one program from using up too much space or causing conflicts with others. Without effective memory management, systems will slow down quickly and possibly crash, especially when running multiple applications. This is particularly important for multitasking and applications that require a lot of memory, like video editing software or games. To get a better understanding of memory management, let's look at some of the main components. Number 1, memory allocation. This is the process of assigning memory to different programs as they need it. The operating system decides which part of the memory to allocate to each program. These are two types of memory allocation, static and dynamic. In static allocation, memory is assigned at the start and doesn't change. Dynamic allocation, on the other hand, adjusts based on the program's needs. Number 2, memory protection. Memory protection ensures that one program doesn't accidentally interfere with the memory allocated to another. This is essential for system stability, as it prevents bugs or crashes in one application from affecting others. For example, if you are running a video game and a web browser, memory protection ensures that they stay isolated. Number 3, swapping and paging. Swapping and paging are techniques the operating system uses to manage limited memory. Swapping moves data between the RAM and the storage to free up space when the memory is full. Paging divides memory into fixed-sized chunks, called pages, which can be loaded or unloaded as needed. These techniques allow the operating system to swap out parts of applications that aren't actively in use, so more programs can run simultaneously. Number 4, virtual memory. Virtual memory is a technique that allows the system to use more memory than it physically has. It works by combining RAM with storage to create a large pool of memory. The operating system creates an illusion of a vast memory space, giving each program its own virtual space to work with. Finally, memory allocation is the process of freeing up memory when it's no longer needed by a program. The operating system reclaims memory from programs that have finished or don't need as much, which helps optimize resources and keeps the system running efficiently. Operating systems use different techniques for memory allocation. Number 1, contiguous allocation. Here, each process gets a single continuous block of memory. While it's simple to implement, it can lead to fragmentation, where small unused memory gaps appear between allocations, making it harder to fit larger programs. Number 2, non-contiguous allocation. In non-contiguous allocation, memory for a process can be scattered across different locations. Paging and segmentation are examples of this approach. Non-contiguous allocation is more flexible and helps reduce fragmentation, allowing the system to make better use of available memory. Memory management isn't without its challenges. One major issue is fragmentation. Over time, as programs are allocated and deallocated, small gaps start to appear, making it difficult to find large enough blocks for new programs. Fragmentation can slow down the system, and the operating system has to work around it, sometimes by reorganizing memory, a process called compaction. Another challenge is balancing memory usage. Programs can have different memory needs, and the operating system has to make real-time decisions about which processes get priority. This is especially challenging when running memory-intensive applications, where the operating system might need to use swapping to keep everything running smoothly. As a software engineer, understanding memory management is key to creating efficient applications. Knowing how memory works and what's going on under the hood helps you optimize your code to use resources effectively. For example, memory leaks, where an application fails to release memory it no longer needs, can slow down or crash a system. By understanding memory management, you can avoid these issues and write code that is stable and efficient. Memory management is also essential when developing for embedded systems or mobile applications, where memory resources are limited. Writing memory-efficient code helps ensure that your app runs smoothly on devices with lower memory capacity. Memory management is the backbone of any operating system, helping keep applications organized, efficient, and isolated. From allocating memory to managing virtual memory and dealing with fragmentation, the operating system uses several strategies to handle memory effectively. For software engineers, understanding these concepts can make a big difference in building reliable, high-performance applications. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you don't miss any future videos. Thanks for watching, and I will see you in the next one, inshallah. Assalamu alaikum.